Hello Math 1100 students, welcome back. The second half of this course will cover just two chapters, Chapter 5 and Chapter 6. In Chapter 5, we're going to study polynomial functions and rational functions. In Chapter 6, we're going to learn exponential functions and logarithmic functions. Those four. Among the big four, the polynomial functions come first, and that's where we're going to begin. So here we go. The definition of the polynomial function, it goes like this. A polynomial function is a function defined by a polynomial expression of one variable like this. Now, as for polynomial expression and what do we do with these, especially about polynomial division and division algorithm, if you need some reminder, please go back to section 0 and have a bit of a review. I prepared appropriate review videos as well. If you feel comfortable, let's just go ahead. Now, as for any function, let's begin with the domain and range. The domain of the polynomial function is always negative infinity to positive infinity because, look at the definition here. The definition involves only the addition and multiplication. No division, no radical. Consequently, there's no room to go anything wrong, like dividing by 0 or putting negative numbers inside of the square root or things like those. This is always valid, therefore, all real numbers. Now, the range, on the other hand, that's entirely different matter. Here are some examples. It turns out that if n is even, the degree is even, and the leading coefficient is positive, then we have this kind of range. We have the absolute minimum here, and then upward, it'll go on forever. So we have this kind of range, from m to positive infinity. Now, if n is even, that is, the degree is even, and the leading coefficient is negative, then it's the other way around. Just flip it, and that's an example. We have the absolute maximum here forming, and then downward it goes on forever. So we have this kind of range, negative infinity to capital M. What if n is odd? That is, the degree is odd. In that case, always the range is negative infinity to positive infinity. We have more or less decreasing like this, or we have more or less increasing like that. Either way, negative infinity to positive infinity. Now, as for the reason behind all these, we have to answer it in the next section when we deal with the end behavior of the polynomials. Okay, here we go, and we need some preparation. And the preparation here is a little bit theoretical, and it's going to be difficult to understand for most students. But please be patient. At some point, it's going to click. And once you go to computation, once you go to actual problem solving, it's going to be easy. All right, here we go. Patience, please. We say a pair of real functions f of x and g of x are asymptotically equivalent if the ratio between these functions, f of x over g of x, gets close to 1. Gets close to 1 as the absolute value of x gets large, which means as x gets humongously positive or humongously negative. Let's take a bit of a time out here and have just a little bit of digression. What if the ratio f of x over g of x is equal to 1? It says close to 1, but what if equal to 1? Then f of x and g of x are the same. Do you see this? If the ratio is equal to 1, multiply out this g of x to the other side, then we have f of x equal to g of x here. So equal to 1, then we have precise equality. Now this is not precisely equal to 1. It says close to 1. So approximately equal to 1. In that case, we have asymptotic equivalence. Wait a minute, what's the difference between this and that we have a double dash here, kind of like weakly equality sign, and then this was single dash. What's the difference between the two? The single dash here, asymptotic equivalence, means the ratio gets close to 1. And double dash here, approximately equal, means the difference is close to 0. So there's a subtle difference between one and the other. Let's go back. F and G are asymptotically equivalent, or later on in section 3, locally equivalent. That means the ratio gets close to 1. Approximately equal, that means the difference is close to 0. Subtle difference between one and the other. Oh wow, it's getting really deep. And there's a reason why this is getting really deep. It's coming from calculus, that's why. So I don't blame you if you have a little bit of difficulty understanding this concept. But the concept may be hard, but the computation will turn out to be easy. Because, pay attention here now, this is all you need to do. So, the asymptotic equivalence computation we have to do in this course is basically just disregarding all the lower degree unimportant terms and simply taking the leading term. That's the only thing you have to do here in this course. So it's an easy computation. Conceptually, it's not easy. It's difficult. You need this ratio idea and the subtle difference between equivalence versus approximation. And of course, concept regarding calculus. It can get really deep, but in terms of computation, in terms of problem solving, it's easy. All you have to do is to take the leading term. Now, why does it work like this? And what are we trying to accomplish here? Basically, what we want is to establish the end behavior of this polynomial function. That is, the behavior of this function as x gets humongously positive or humongously negative. But then again, this function, original function, is too complicated. So I'm going to find out a much simpler function that shares the same behavior. And that function is the power function given by the leading term, simply by crossing out all these. And as for the power function, we know an awful lot about power functions. When n is even and leading coefficient is positive, then U-shaped, like this. And then when leading coefficient is negative, then flip it over, it's going to be upside down U-shaped. Look at this visualization. Original function is polynomial and is complicated. It's blue graph here. And the red graph here is the leading term, just a power function given by the leading term. So it's really simple here, just U-shaped. These are two different graphs, yes, but if I go humongously to the positive or humongously to the negative, as you can see here, and then eventually there, these two graphs became kind of indistinguishable. They share the same end behavior. This one, complicated. This one, easy. But they're the same. So what can you say about this polynomial function? Just disregard lower order terms and then answer everything about the power function given by the leading coefficient. That's it. That's all there is. Now, why do we do this algebraic computation using asymptotic equivalence when we can simply graph it? Actually, that question will be answered the next week when we deal with the rational functions. There, the asymptotic equivalence computation will turn out to be extremely useful and important. Here, it kind of looks gimmicky. And then we have to deal with some theory. But please get over with this initial resistance. You're going to get used to this quickly. By the way, here's another example, this time odd degree. So, throw away all the unimportant terms and then simply take the leading term, y equals to negative 2x to the 5th power. Compare those two graphs. Polynomial graph, that's green and that's complicated, far more wiggly, and a little bit larger scale and then much bigger scale. Now these two are indistinguishable. So that's how we have the end behavior. So if you want to find out the end behavior of a polynomial function, throw away all these and then look at the end behavior of the leading term. It's that simple. Okay, do we have enough time for some exercises? Okay, here's one. Find a power function that shares the same end behavior of the given polynomial function. Oh, that's really easy. Discard all those and then you get y equals to negative 2x to the 4th power. Too easy, isn't it? And the graph should be upside down U-shape. Negative and then 4th power. That's it, and here's a graphical justification. Okay, brown is the original polynomial function. It's complicated, as you can see. But as you go to the larger scale and much larger scale, they became kind of indistinguishable. Asymptotically equivalent. And then the red graph, the simpler graph here, we know an awful lot about that. It's upside down U-shape because this is negative times x to the even power. Okay, how about this one? A little bit more challenging, but actually the same idea. Let me copy and paste this entire thing. Oops. Okay, let's start from here. Now we're taking the asymptotic equivalence, so the highest degree term wins. So we have x plus 1. We just regard plus 1 and just take the highest degree term. X minus 3, again minus 3, gone, and we just have x. And 2x plus 5, I'll simply take the leading term here, 2x. X squared plus x plus 3, again, just a leading term only. And then what is this? And that's negative 2 times h, so negative 16x to the 1, 2, 6, 4, 10th power. So there you go. This function behaves pretty much the same as y equals negative 16 x to the 10th power in larger scale. And this one is pretty simple. It's a power function, even power times negative number. So this is going to be upside down U-shape. Let's see. Yes, indeed. So that's how you can get the power function that shares the same end behavior as the original polynomial function. Now, at this moment, this kind of computation may look a little bit gimmicky, but believe me, it's going to become really useful next week when we start dealing with the rational functions, when we have numerator and denominator and so on and so forth. Okay, so much for sections 1 and 2, and we'll meet again in section 3.